Okay, today is 6.2 polynomials. We're going to review 6.1, but the official new lesson is called 6.2, and it involves the remainder theorem and the factor theorem, but it also really involves a lot of other things that I'm going to be talking with you about, like we need to know limits. I'll teach you that, and we also need to be reminded how to use synthetic to do factoring. So hardcore factoring can be done with synthetic. You did this last year. You did not do limits though, so that's a brand new thing. So quite a few little things to learn for today. But let's first start with something you should be much more comfortable with. If I gave you this picture, can you tell me what degree this thing probably is? Definitely not a degree 3. I can tell because there's 4 roots. So it's got to be at least a 4 or more than a 4. So any thoughts? What do you think? Probably degree 4. Degree 4 would make sense because it's an even and they're both going down. You remember that they have to either both go down or both go up if it's even. If you didn't know that, you should write that down. If they're odd, they're going opposite directions. One ends up, one ends down. Okay, this is definitely an even. And it has 4 real roots, so obviously it's at least 4. What else could it be? It could be 6, it could be 8. How come it has to stay an even number like that? Because every extra set of roots you have is a set of a plus and a minus something, because it's like in the quadratic formula, plus and minus the square root of. Anyway, those imaginaries always come in packages of 2. And it'll keep it even because they have to both be either down or up. And we know it's even because they're both down. Okay, next, I can tell what the y-intercept of this thing is. If I had the equation, the y-intercept is where what? X equals 0. You just pop in an x equals 0 to get it. All right, so let's give you one where you have an equation. Y equals, and let's say we had x minus 5 and x plus 4, but it's squared right there. Would you make me a little sketch of what that would have to look like? You know the 2 roots, also known as the x-intercepts, also known as the zeros. And you should know how the story ends, whether it ends positively with everybody happy, hugging the little pony that's on their new ranch that they just won, or it could end badly with the semi-truck and the unfortunate crying. And okay, so is this one ending happily? Yes, it is, because it's positive in front, so I know it's going up here. Let me tell me something else you know. Yes, sir. 5 and negative 4. I would agree with you. I'm going to call that 5. I'm going to call this negative 4. Okay? Tell me something else you know. Yes, sir? Cutting through at 5. So if it has to be going up on the end like this, and it has to be cutting through at 5, I may as well just have it cut right through right there. Okay? Tell me something else you know. Yes? On the left side, it has to go down. I would agree with that. Because why? Yes. Once you multiplied it all out, it would be x to the 3rd, and therefore it's degree 3. You don't just pick the biggest one. On this kind, you have to think, if I multiplied this all out, what would be the biggest degree? And it's degree 3, and therefore they must go opposite directions. One's up, this one must be down. What else do you know? Yes? It has to bounce at the negative 4. So I'm going to move this over, and if I say it's going to go down, that's a little too straight down. I better round it off a little bit like that. There we go. And then I can just connect those two. Now, what would be smart to check? The what? It's one of my favorite sayings. The y-intercept. Because the y-intercept is where x equals 0. So if I stick in a 0 quick, do you get that this becomes 16 times negative 5? Would you agree it's some really big negative number? And therefore, did I cross at a negative number down here? Yes, and therefore it's okay. That is a sign test. I tested in this little region here, between here and here, to see if it was negative or positive, because the y-intercept is easy to see. Could I have tested this other end with like a 6 to test if I did it right? Certainly. I could stick in a 6 instead of a 0, and then it would become a really big positive number. and another positive number, and a positive times a positive is a positive, and therefore it should be up here, not down here. So good. I tested it, and I made sure it was actually positive there, and it was. All right. But I think the best place to test is the y-intercept. All right. Now, that was an easy one. But let me ask you some questions about it. What are the zeros? And what is the multiplicity? And what action, like things like snake or whatever, is happening at said zero? We already talked about what degree this is. This is one's a degree 3. What's the zeros? Well, tell me, what are they? -4 and 5. That's nothing complicated there. How about the multiplicity? What the heck is that talking about? Well, the multiplicity at the -4, that's a bounce, so I'm going to write bounce. That's an action. The multiplicity, come on, somebody pull it out. Yes? Yes, the multiplicity is 2. That little number is the multiplicity. The multiplicity is a number like 1, 2, or 3. It's like a bounce is 2, a snake is 3. The other ones are called cut-throughs. They're the 1s. Those are the 3 ways that you can interact with the x-intercepts. All right. So now, everybody stand up. Stand up. Stand up. All right. Now, you're an odd function, and you have a happy ending. Please put your arms in the appropriate way. You're an odd function with a happy ending. No, your point of view. I'll stand this way if it helps you. You're an odd function with a happy ending. Were you like this? Okay, good. Next, you are a even function, and I don't know what your lead coefficient is. Now, what should you do? You're an even function, but I don't know what your lead coefficient is. Very good, Yana. It's this or this. I don't know. It's this. Okay? How about this? You are an even function with an unhappy ending. All right, nice. Oh, I love how you did the bow-legged thing too. Okay, now you are a 5th degree function with a lead coefficient of -2. You're a 5th degree function with a lead coefficient of -2. All right, what is that lead coefficient of -2 telling you? The ending, which is what? It's bad. The bad ending's going down, okay? And since it was a 5th degree, then they must go the opposite direction, so you should have been like this. Okay, good, thank you. I really did that because somebody was sleeping, and now they're not anymore. I won't say who. All right, and it was also good practice. All right, now, go back to this. This 0 of 5 has a multiplicity of what? 1, good. It's just what degree it's at, see? That little term right there. And then the action, we call that a cut through. Okay, good enough. Now, here's a harder one, because you're an honors pre-calc. Make me a sketch. Tell me its degree. Tell me the zeros, the multiplicity, and the action at each 0. I'll pause for a second when you try that. Okay, here's some thoughts. Did you realize that at the front here, this was its own separate root? If you didn't, I'm going to just put a parenthesis around it, and maybe you'll see that it's just like all the other things. It gets its own separate root. This one was -2. This one was 4. What's that one? 0. All right. So here's -2. Here's +4. And there's another one at 0. Those are the 3 roots, also known as zeros. Okay? Now we know the ending of the story is sad. It's going to be going down on the right. And we know it's got to have a triple root, a snake, at the -4. Total degree is 3, 4, 5. Do you get how I got a degree 5 out of this? Raise your hand if you also had degree 5. Okay, good. Now, if I'm sketching this thing, one of the things I look for is, like, where am I going to do special stuff and where am I just going to cut through? So since I know this is a cut through on the right hand, no, this is the snake. It's a snake on this right hand end. I'm going to have to take special pains to draw my snake in a way that I've got an inflection point there. And I might even label it with snake, just in case my artwork was terrible, but the teacher would understand what I meant. And then I have to figure out what I'm doing at the other spots. It's just cut throughs here and here. Cut through at 0 and a cut through at -2. So I can cut through this here, I can cut through that there, and then I should stop and look at the end and see if it makes sense. Does this look like a degree 5 based on its ends going in opposite directions? Does it look like it's got this ending of the story right? Okay, and does it look like it's doing the right thing at each 0? Well, that's where I can list them out. My zeros were -2 and 0 and 4. And the net multiplicity is just power here. So the power at the -2 is a 1. The power at the 0 is a 1. And the power at the 4 is a 3. And what are they doing then? 1s are cut throughs. And the last one is a 3, which is a snake. If you used other words to describe it, yay, as long as I can tell you meant that it makes the snake shape. All right. How many of you feel like you nailed that one? Okay, good. So now, where do we go from here? Well, that's about as tough as we get with the, like, knowing how the sketches should look. But how do we describe a sketch that looks like this? Let's say it's down on the left end, and on the right end it's up. There's an official mathematical way to describe that the ending is going up or that the ending is going down. Or sometimes the ending of a function levels off. Let me show you one of those. Let's say I had a graph called the basic logistic function. Do you remember me showing you this graph before? And it levels off at some number, like let's say 8. And on this end, it's going towards an asymptote that would be right here at 0. So that one's stuck between 0 and 8. So if I go way to the right, it doesn't end up going towards infinity or negative infinity. It goes closer and closer to 8. And if I go way to the left, what does it get closer and closer to? 0. Good. Okay. So there's ways to mathematically describe those. They're called limits. This is your first limit. It's kind of like last year you did your first log problem. Okay, and then you'll do logs again in this class, and you'll do logs again in calculus. Okay, you did your first trig problem. It was probably in your geometry class, I'm guessing. You probably did sine, cosine, tangent for the first time in geometry. Okay, well, this is one of those big moments. You're doing a limit today. And a limit is just a way to describe how something is going to end, where the function is going to be at the end, on the right end or on the left end. Okay, there's even more complicated limits, but for today, we're only going to describe it. Do you get, if I just asked you verbally, how does this function end on the right? You could say, well, it's going towards infinity. It's just like that, except you're saying it mathematically. Or where does this function end up on the left? Again, I should cover up the other one for a second here. So, I'm talking about the red one here. Where does this function end up on if you go way to the left? Negative infinity, okay? So here's how you say it mathematically. You better write this down. Lim of f of x What do you think that stands for? Limit of the function. Okay. The limit of the function. Now let's just talk about what that like means, a limit on something. Let's say that you are a professional baseball player, okay? And they have pretty strict rules in the players union about what salaries can be. They have a minimum, like the lowest that you can pay somebody to be in the pros, okay? Do they have a maximum? No, not for any individual player, but they do have a max for what? For the team. They have maxes for the team because basically they don't want one team to be able to buy all these really expensive players and just dominate. Okay, so they want to say the most you can spend as a team is whatever. So they have a limit at the max you can spend as a professional baseball team is this much per year on salaries. Okay, but they could give it all to one guy if they wanted. Well, they couldn't actually because they have to have minimums at least for the other players. All right, but they give most of it to one guy if they want to. All right, so the limit on this function, there is no limit on this function. So they'd say that the limit as it approaches infinity, what am I talking about there? That's where x is infinity. This is x. As I get closer and closer to infinity this way, then the answer to the question is not the x. We already know the x is getting towards infinity. What we want to know is what will the y be? And in this case of a graph, it's the height of the graph. The height of the graph will approach infinity. I just gave the mathematical description you will have to use on your AP Calc test someday. And you have to show it that way. You can't write it out in words. The limit of this function as x gets closer to infinity. If you wrote it out in words, they won't give it to you. You have to know that format. And I'm going to note here that the lim, underneath the lim is where you write x goes to infinity. If you had written this on the AP Calc test as this, of f of x, they will mark it wrong. You can't have it in that format. That is not how a limit is written. You have to have the x goes to infinity underneath the lim. Okay, I want you to think it through, and I bet you now you can write your first limit on your own. Write the limit for the left end of this function. Remember how I said it always starts with this part. Every single limit statement you ever write will have those parts to it. That really means you just have to know that, which is the x, and that, which is the y. It's not a hard one. It's not a hard concept. It gets tougher when you have limits on weird situations. When the graphs are just doing the end values, it's not hard. Do you get the limit in the middle of this graph? It would be more complicated because then it kind of depends on where you're headed towards and how far you go towards it and which direction you're coming from. It gets more complicated in the middle. But for right now, we're just doing the ends. Yes, sir? You don't need to write. No, you do not need to write the word height. So here's your final answer. Lim of the function as x approaches, in this case, negative infinity. Excellent. As we're going this way forever. Okay. When we get forever that way, the graph will be the height of forever that way. Negative infinity. Raise your hand if you had that one right. Okay, good. Now, let's see if you really understood this. This is the state of the art. Write me a limit for that one on the left and the right. There's a left end limit and a right end limit. Remember what I said always has to be in your limit statement. Because once you realize you only have a choice on two things in your limit. Everything else is boilerplate, has to be there. Limit of f of x as x approaches, and the equal sign, you have to have those. Then you just have to fill in two things. And I bet you more than half of you will get this right. So that shows it's pretty easy. Doing my left end. And And then I'm going to make a point by cloning this sucker. Clone. Identical over here. See? It's just the X number might change and the Y number might change. Mr. BG. Were you actually an original member of the BGs? You were from birth, actually. All right. Go ahead. What do you get on the left end? As X approaches 0, or do you mean that the answer is 0? Okay, so what should be by the X approaches? What is X approaching if you go on the left end of this function? Yes. And the answer was? 0 is correct. Very nice. Negative infinity and 0 were the two things you should have plugged in there. Why is X negative infinity? Because X is way over here on the left end. Infinitely far that way. Negative infinity. Raise your hand if you had that one right. Okay, good. On the right-hand side, let's go with in the corner pocket. Mr. PA. Limit of the function as X approaches. Yes. That means you're way to the right. And the height will be when you get there. Oh, good point. You just say 8. But I know you're thinking it can't get to 8. But then again, you can't really get to infinity either, can you? Okay, so this is important to understand. This is about approaching, like we're getting close to. You can't get to infinity, and you also can't get to 8, really. But you can get infinitely close to infinity, and you can get infinitely close to 8. So this is all about getting close to. But please don't write like 7.999 or something like that. No. You say 8 because this is a limit is about what you're getting close to, not what you're actually getting to. How many of you had that one right? Good. So now, here's how you put it all together. I'd like to know the left and the right end limits to this function. If I were you, I'd make a little tiny sketch quick. Just a quick sketch. Don't even need to know exactly what happens in the middle. All you care about is the right end and the left end. You know what I mean? Because how it makes its little curves in the middle, it's kind of irrelevant. It's how it ends. The left and the right end. Okay, I get it would take a while to do an accurate sketch. We don't need one. We need to know how the story ends and how it begins. Okay, the ending of the story, it's got this negative at the end. It's got an unhappy ending. It's going to be going down on the right. And since it's degree, what, 6, they must be the same. And therefore, if one's down, the other must be down. And therefore, it's down and down. So that's all I needed to know. Now I can write my limits. Now I say lim of f of x as x approaches. If on the left end, what am I x approaching? Negative infinity. And that will be, when I get there, how high will the graph be? Negative infinity. That's because it's this end, and it's going down as we go further and further to the left. As I go further and further to the right, it's also going down. So can I just copy this exactly? Not exactly. The limit of the function as x approaches and equals, that's how you always start. Here's some And what was x approaching? Yes. How about this? If I ask you for the left-hand limit, you could always say x is negative infinity. All right. And if I ask you for the right end, x is always approaching infinity. So then really all you need is one number, and it's really the height of the graph on the left end and the height of the graph on the right end. Okay. You've learned limits. Cool. They get more complicated, but I'm not going to mess with your head today because we have another thing to learn. So if we have something complicated like, for instance, this, x to the third, write this down, please, 6x squared minus x minus 30. Believe it or not, you're not as smart as you used to be. Because in honors higher algebra, you had this question, and you almost all were able to do it back then. And you could factor this, if I just said factor it. Okay, but you've probably forgotten. I did give you a little preview at the beginning. I said the words. Does anybody remember what that method is that factors this thing? Synthetic. Synthetic. Synthetic division. Let's talk about a division in this context. So if I was dividing 80 by 2, do you get that that's the divide sign? Okay. But do you get, when I do that, I'm breaking it up into its factors. I'm saying that 80 breaks into two things, 2 times 40. So my answer to this division problem is 40. And what I'm really asking then is, could I find 2 times something that would make 80? And the answer is yes, and the answer is 40. Okay, you're factoring it. So if I ask the question this way, does 5 go into 100? So really I'm asking you to factor the 100 into 5 times what? Do you know it? So the answer to this is that, yeah, it factors, and it's, not 2, sorry, 5 times 20. So is 5 a factor of 100? Yes, it is. And the other factor that goes with it is 20. It's kind of like that when I say, here's a big complicated thing, and I want to know is, let me see if I did this right. Is 2 a factor of this? Well, if 2 is a factor of this, then that means that, be careful now, what do you think goes in there? X minus 2. Okay, and if 2 is the root, the 0, the x-intercept, then the factor is going to be x minus 2. Do you get how those kind of go together? They're opposites of each other. So if 2 is the root, then x minus 2 would be the factor. X minus 2 times something will equal that then. That's what we're trying to figure out, is does that work? Can we factor out an x minus 2? And in the end, the answer for this thing will come out like maybe, x plus 7 and then x minus 3 or something, okay? But we're not going to try to factor it all the way at once. All we ask is, would this work? Could you put 2 into this function? So if the question is, if 2 is a root, then we check x minus 2 is the factor. All right, so does this ring a bell? Does 2 go into the blue thing there? So then you go, does 2 go into 1, 6, negative 1, and negative 30? Probably the only time in the school year I can reference Snoop Dogg and drop it like it's hot. And then we multiply, and then we add, and then we multiply, and then we add, and then we multiply, and we add. And if at the end, whatever we get at the very end, that's the remainder. And if there's no remainder, then it went in perfectly. Let me just show you what we're doing in the context of numbers again. Let's say we said, does 2 go into 7? Does 2 go into 7? Sure it does. It just has a remainder. So when it has a remainder, you're really saying that, no, 2 doesn't go in. Well, 2 does go into 7. It goes in there a bunch of times. How many times does it go in? 3 times, and there's a remainder of what? Okay, so when we say does 2 go into 7, there's kind of two answers. There's either does it go in nicely and have a remainder of 0, or does it go in with a remainder of like 1? Well, 2 goes into this thing. 2 can go into anything. 1 can go into anything. 5 can go into anything. But it's just whether or not you're going to have a remainder at the end. That's the remainder theorem. Okay, the remainder theorem is basically saying if you divide by something, you're going to get a remainder. What happens if the remainder is 0? Then it worked out perfectly. And you have factored it. Okay, so if 2 goes into 7 3 times, I get 6, and there's 1 left over. That's a remainder of 1. And then technically, the answer is 1/2. Do you get how 3 1/2 is what the answer is? And that's because I took this divided by this. All right, so back to my synthetic. I'm seeing, I know 2 will go in. It's just a matter of whether there's a remainder or not. What part tells you whether or not it worked? The remainder. Where's the remainder? At the end. At the very end, if you get a 0 at the very end, that means there was no remainder. And therefore, it worked perfectly. And therefore, you can factor with that. All right, so you drop it like it's hot. Then you multiply. Then you add. Do it with me, please. 1 times 2 made the 2. And then 6 plus the 2 makes the 8. And then now what do you think we're going to do? 8 times 2 is 16, and then we add them. What's negative 1 plus the 16? 15, and then we multiply. 50 times 2 is 30, and that worked out perfect. We have a remainder of 0. And since it has a remainder of 0, it worked, which means we just factored it. So what's the answer? The answer then, drop this down, is, remember, it's not a plus 2. It's x minus 2 is the right factor for this root. And then this becomes my other factor. Do you remember how this works? Who can tell me where to put the rest of my stuff? Yes? 1x squared, 8x, and plain old 15. And there is what that times that will make this. So is it factored? Yes. Is it factored all the way? No, because we could probably factor this again in most of our problems. I'm going to rewrite x minus 2 here. And now this is baby factoring. X, and what multiplies 15 and adds to 8? Plus 3 plus 5. There we go. Yay. We factored it. Factored it all the way. Does that make sense? Okay. So here's a question for you to see if you really understood that. Pause for a second. One last time. X to the third plus 3x squared plus x minus 3. And if it equals 0, then if you could factor this thing, you'd have the roots. You'd have the zeros, the x-intercepts, the solutions to it. So if you could only factor it, well, I am going to tell you something that would go into it. I'll tell you that I think that 1 is one of your roots. 1. If 1 is a root, just remember that at the end, the factor for that will be x minus 1. But I said 1 is the root. If 1 is a root. Now, do you get how I translate this into a 1 and a 3 and a 1 and a negative 3. Okay, so 1, 3, 1, negative 3. Now, ask Snoop Dogg how to start. Multiply, add, multiply, keep going. Did it work? All right. If it didn't work, what did we prove? That 1 is not a root. All right. That means that when you actually factored it, you must have had a remainder at the end. Okay. So I'm going to pause for a second. We're going to change one number, and I bet you this thing will work. Okay. Now we're going to change one little sign in our problem. I want to erase this one and just use the same exact problem, and instead of a plus, we make that a minus. Now I bet it's going to work. Now see if 1 is a root. Again, it happens, even on your homework, that you're going to have ones that won't work. They'll give you a remainder at the end. If they have a remainder at the end, then it wasn't a root. Anybody verify this one worked? Yay. Now, if it did work, then tell me what, if you can factor it, you should be able to factor it all the way. It's not just about, yay, it works. It's about what is the answer? What are the factors of this thing? What can you factor it out to? Okay, so you should have said if 1 is a root, I'm going to use 1. And I'm going to put a 1, a 3, a negative 1, and a negative 3. Drop it like it's hot. 1 times 1 is 1. Add them, 4. Multiply them, 4. Add them, 3. Multiply them, 3. Add them, 0. Yay, it worked. But now, this is the really important part of the interpreting. This 1 comes down and becomes part of x minus 1. Because if 1 is the 0, when I put it in, it should make this thing equal 0. So that means I need a minus 1 there. Okay, then this part becomes x squared and x, and they're all positive, so it's plus and plus. Yay. Can I just stop right there? Oh, it's a common mistake. You do all that work, and you know that it's factoring, but you haven't factored it all the way yet. Then I got to factor this part the old-fashioned way, x plus 3, x plus 1. There we go. I have factored it all the way. I know all the roots, and I know they're all cut-throughs. And I know it leads with a positive, and therefore it's happy ending. It's going up on the end. See how much you've learned and remembered? Okay, so that's all you need to be able to do your homework for tonight. You may notice that I made the judgment call to not try to teach you one more thing, which is long division, which is the comparable thing to this. Going, okay, 3 goes in here how many times? 9, and it makes 27, and then you multiply those out and it comes out to 0. You can do that like this. Going into x squared minus 4x plus 3. You can do long division like this too. And I think you did it last year. Probably depends on your teacher, whether or not you did long division or not. But that's what we're going to have to do as our very last little thing I add to this tomorrow. Okay? Then you will have that one more little tool in your tool bag. But synthetic is better, faster, and used more commonly anyway. So you could probably live with not knowing long division, but I'm gonna make sure you know it, because I don't want any of those. I want to be able to say that you know everything that past year's students have known, and that's one of the things they have conquered last year in honors pre-calc, and the year before that is long division of polynomials. But I'll show you that tomorrow. So today's assignment, as we went over before we started, I have cut it down a smidge. Everybody look at day 1 here, number 1, and it's written weird. Yeah, I know. But you can do synthetic instead of long. And do you see how I started it by saying instead of x minus 3, I used plane 3? Remember how those have to be opposites of each other? If it says x minus 3 as the factor, then the root is 3. And I know some of you are going to go through and say, but it didn't work. Well, that's good information then. And then what's the answer? Well, the answer is that it didn't work. It was not a factor. There is a remainder. All right. So then I suggested again, until I teach you the polynomial long division tomorrow, that is not as important as a synthetic. We're going to put off these long divisions until tomorrow. Here we go. This is the synthetic area. So 7, 11, and 17 are more likely to work out nicely. I did give a hint on number 11. Do you remember from last year when you did this stuff that you had to have placeholders? If there's no x squareds in this, do you get how there isn't any x squareds? I have to write plus 0x squared. And there's no plain x's in here either. So I had to write plus 0x plus 8. Then these numbers, the 1, the 0, and the 8, go here. So you might need placeholders here and there. When it's all done, though, don't just fall into the trap of thinking, oh, it ended with the 0, I'm done. You have to actually factor it all the way then, whatever your answer comes out to. So this minus 2 goes back to an x plus 2. See, so what they were asking. And then you got to figure out what goes in here. All right. Do number 23. Skip 25. Only do number 37. And this is just synthetic again. And it feels weird to have a 1/2 in the little box, but there's no reason the 1/2 can't be in there. You can multiply by a half. It's really not hard to multiply by a half. All right, and then this one. This is a good question. Remember how we challenge you by throwing in a letter instead of a number, where you usually would have a number right there? You got to admit, I'm not giving you all the super hard stretcher problems. I'm giving you a few. That means you should be able to tackle them, figure them out, stretch your mind. Got to be able to handle hard problems. All right, and that's all we have for you for today. I know it's a long day. We have to be able to get through a lot of material by testing on Monday. And the only reason we're rushing like that is because we have to get through another unit by Thanksgiving. And if we didn't rush this unit, we wouldn't have made that one unit. And then you'd have had to test after the Thanksgiving weekend, which would have been pretty bad. You got to admit, you'd rather probably get your test done and have no homework over the Thanksgiving weekend than to have us go slow here and then have to test after Thanksgiving. Okay, and that's all I got for you.